Good day everyone, welcome to our video presentation. Today our group will be presenting an experiment on hydraulic jump. Before we begin, let us introduce ourselves. Our group consists of 5 members as shown in slide. Now, let's begin our presentation.
For introduction, a hydraulic jump occurs when rapid turbulent water transitions from a high velocity supercritical state, which is Froude number is greater than 1, to a slower, deeper subcritical state, which is Froude number is less than 1. This phenomenon is highly valued in engineering for energy dissipation. As the water suddenly slows down and rises, its kinetic energy converts into potential energy, while turbulence safely releases the excess energy as heat. Engineers intentionally force these jumps using channel registers to reduce downstream velocity, ultimately protecting hydraulic structure from bed erosion. The objective is to analyze the flow pattern and look into the characteristics of a hydraulic jump created as water flows beneath an undershot weir. Next, we found 4 problem statements. Firstly, water and other liquids flow over smooth surfaces before suddenly deepening. Secondly, the fluid's velocity changes as a result, creating a turbulent flow pattern. Thirdly, examine the hydraulic jump and take measurements of its depth, flow rate, energy loss, and Froude number. Lastly, measure the appropriate parameters and comprehend the physical principles that support the hydraulic jump.
Next is the basic concept. The basic concept of a hydraulic jump is the sudden transition of water flow from a high velocity, shallow flow called supercritical flow, to a low velocity, deeper flow known as subcritical flow. This transition creates turbulence and dissipates excess energy. The flow condition is determined using the Froude number. Hydraulic jumps are important because they help reduce flow velocity and prevent erosion in downstream hydraulic structures.
Next, I will start with the methodology. This is the apparatus that I used for this experiment.
Now, I will explain how the hydraulic jump experiment was carried out. Firstly, we need to adjust the sluice gate to obtain the desired flow condition before taking the measurement. Then, all the main power switch was turned on to start the water flow. The rectangular flum was mounted securely onto the hydraulic bench. Next, we need to measure the flum width. Next, switch on the hydraulic bench and to allow the water to flow through the rectangular channel. We can adjust the flow rate using the control valve until a clear hydraulic jump is formed in the channel. We wait until the water flow becomes stable before taking any measurements. After water is stable, we measure the height of the sluice gate. Then we measure the height of the Y. After that, the height of Y1 is measured before the water jumps. And the height of Y2 after the water jump is also measured. The distance is also measured between water jumps until the water is in a stable state. After completing all the measurement, the pump was turned off. Then the time taken for the water flow to stop completely was measured using a stopwatch and recorded. All the steps and measure repeated in the 3 times.
Based on our calculation, the discharge increased from 0.001139 in experiment 1 to 0.001838 in experiment 3. As the discharge increased, both the upstream velocity V1 and downstream velocity V2 also increased, showing that a higher discharge produces a faster water flow. The Froude number also increased, but all values remain below 1, indicating that the flow stays subcritical and relatively stable throughout the experiment. We also found that the specific energy before the hydraulic jump E1 was always higher than E2. As a result, both the energy loss and power loss increased with discharge, meaning more hydraulic energy was dissipated through turbulence. Overall, this result showed that increasing the flow rate lead to higher water velocity and greater energy dissipation. This is the main purpose of hydraulic jump, as it reduces excess flow energy and helps prevent erosion and damage to hydraulic structures downstream. In real engineering application, hydraulic jumps are widely used in spillways, dam, canal and drainage system to improve safety, reduce corrosion and protect the surrounding infrastructure. This agreement is closely related to Sustainable Development Goal 9 (SDG 9). By understanding how hydraulic jump dissipates energy, engineers can design more efficient, durable and resilient water infrastructure. Better hydraulic design help reduce maintenance costs, improve long-term performance and support sustainable water management for a growing community.
Finally, in conclusion, the objective of analyzing the flow patterns and characteristic of a hydraulic jump beneath and under shock weir was successfully achieved. The experiment showed a clear transition from supercritical to subcritical flow, with energy water depth increasing from H1 1.2 cm until 1.5 cm to H2 1.1 cm to 4.4 cm, and notable energy dissipation observed through the calculated specific energy loss. This confirms the basic concept of a hydraulic jump, where a standing wave forms with intense turbulence, converting kinetic energies with potential energies. The result validates the important role of hydraulic jumps in energy dissipation and protection of hydraulic structures and erosion. That is all for hydraulic jump.